we will continue our discussion on principle of hydraulic machines and system design. We have discussed about radial equilibrium for axial flow machines, and we have derived the equation when radial equilibrium is attained, considering incompressible flow as well as compressible flow, and eventually have arrived at that when pressure is not changing, total pressure is not changing along the radius, then what is the radial equilibrium equations. And from there we have discussed a case when the flow is a free vortex flow. That means whenever a flow is flowing through an axial flow machines and flow is free vortex flow, what is the velocity distribution, that is axial velocity distribution in the axial direction as well as the radial direction. Today we will discuss another case where the flow is force vortex flow, and we will solve the radial equilibrium equation to see the velocity distribution whenever fluid is flowing through an axial flow machine. So yesterday we have discussed about a case when the flow is free vortex flow. So today we will see what would be the velocity distribution whenever flow is passing through an axial flow machines for a force vortex flow. So today we will discuss about another case, that is case 2, that is forced vortex flow. Forced vortex flow. So for a forced vortex flow, what will be the velocity distribution whenever a flow is passing through the impeller of an axial flow machines? That is what we are going to analyze. So now for a forced vortex flow, we know that c theta by r is equal to constant. So for a forced vortex flow, we know that c theta by r is equal to constant, let us say k, that is for the forced vortex flow. That is for the forced vortex flow. So this is important, that for a forced vortex flow c theta by r is equal to constant. Now if I try to recall the equation for the radial equilibrium, whenever total pressure is not changing along the radius, then if I try to recall the equation for the radial equilibrium, so equation for radial equilibrium for a case, that is for incompressible flow, and when pressure or total pressure is not changing, rather total pressure is not varying along the radius, then equation is c theta square by r plus half ddr of c r square c theta square plus c z square equal to 0. Because we know that if we draw the again an axial flow machine, then this is the blade, and this is the case where Cr equal to 0, and upstream and downstream Cr not equal to 0. So here Cr not equal to 0 and here Cr not equal to 0, but here Cr equal to 0. That means whenever radial equilibrium is attained, then the centrifugal force is getting balanced by the radial pressure gradient, and the radial Cr becomes 0. So this is the radial equilibrium equation. Now if I apply that, if we try to obtain the velocity distribution, that is c theta and cz, of course we can obtain for a forced vortex flow what should be the distribution of c theta, but what will be the distribution of cz from this radial equilibrium equation, then now I am going to consider c theta by r is equal to constant. So now I will try to write this equation in a bit different form, that is c theta square by r plus half ddr of c theta square plus half ddr of cz square equal to 0. That is the equation. Now I can write these first two terms in a form that c theta, that I can write 1 by 2 r square ddr of r c theta whole square plus half ddr of cz square equal to 0. So first two terms can be clubbed together, and I am writing in the form, probably this is not wrong. So if we take c theta square, yes, r square 2r plus half ddr of c theta square. Now if we are going to consider that c theta by r is equal to constant, therefore I can write that c theta by r is equal to constant. So r into c theta, that is 1 by r square ddr of r c theta square plus ddr of cz square equal to 0. This is the final equation you are obtaining, Now C theta is equal to what? R into k. So it would be C theta will be equal to R into k. So if I put this value 1 by R square into d dr of R square k square plus d dr of C z square equal to 0. So this is the equation. From here I can write that d of C z square equal to minus 1 upon R square k square into R dr. So I can write that 1 by R square into k square R into dr. So that is the equation, final equations d of C z square. So d of C z square is equal to minus 1 by R square k square into R dr. So from there I can calculate. So if I go to the next slides, so we have obtained that d of C z square equal to minus 1 upon R square k square into R dr. So 1 upon R square minus 1 upon R square k square, no, minus 1 upon R square into 4 into R to the power 4. So R cube, that is R cube dr. So it would be equal to minus 4 k square R dr, minus 4 k square R dr. So if I now go to the next slide, then I can write this will be equal to dCz square is equal to minus 4 k square R dr. That is the equations. Therefore Cz square equal to will be minus Cz square is equal to minus 4 k square R square plus some constant, let us say a. Therefore Cz will be equal to root of a minus 4 k square R square. So if I go back to my previous slide where it is clearly written that dCz square is equal to minus 4 k square R into dr and 4 k square R into dr, and here dCz square is equal to this. So Cz will be equal to root of a minus 4 k square R square. So it is seen from this expression, it is seen that for a force vortex flow. So here I write that for a force vortex flow, Cz, that is the component of axial velocity which decreases with radius with the order of. So for a force vortex flow, Cz decreases with radius with the order of k square into R square minus 4 k square. So of the order of k square into R square. So that is in a force vortex flow, Cz decreases with radius with the order of k square R square, but we have seen that in case of a free vortex flow that we have discussed in the last class, that for a free vortex flow that Cz is not function of R, that is Cz is equal to constant. So for a free vortex flow we have seen that if radial equilibrium is attained, then flow through an axial flow machine, Cz is not a function of R, but Cz might change along the axial direction. But in case of a force vortex flow, Cz decreases with radius with an order of k square R square, while since C theta and C theta, what about the tangential component? Since C theta by R is equal to k, that means if R increases, C theta by R is equal to constant. So that means if R increases, C theta will increase. So this is the variation of C theta and Cz for a force vortex flow pattern. That is, for a force vortex flow, Cz decreases with radius, while C theta will increase with increasing r. Now, I will briefly discuss something about the staging. So, you know that sometimes we need to do staging. What is staging? So, if I write that what is staging, that is very important. Sometimes you need to go for staging, that is when a particular pump is not in a position to meet the demand. Sometimes you require higher head or something, then we need to staging is done to rise in the pressure. So, the staging is done to rise in pressure and to prevent shock loss. This is very important. So, sometimes we know that I will discuss today again about this, but again for axial flow machines sometimes we need to go for a staging. That means only to increase or rise the pressure and to prevent shock loss, so that the efficiency of the machine can be increased, so that the efficiency of machine is increased. So, what is staging? Basically 5 to 6 impellers are mounted on a shaft, on a common shaft. 5 to 6 impellers are mounted on a common shaft, and there will be one rotating stator and rotor, just like this I am drawing. So, for axial flow machine sometimes we go for staging, sometimes we need to go for say radial flow machine, sometimes we need to go for a series and parallel operation, that we will discuss in my next lecture. But staging is done to rise in pressure whenever it is very difficult to meet the demand of the system. So, we need to go for staging, that is 5 to 6 impellers are mounted on a shaft, while there will be a stator part that is hanging from the casing. So, if I draw the schematic again now, suppose this is the axial flow machine. So, there will be some stator, and there will be one similar thing will be here, that we will have so this is known as stator and this is rotor. So, rotor is rotating with shaft. So, rotor is rotating with shaft and stator is fixed with casing, as I said, fixed with casing. So, as I said that sometimes staging is done, that means this is 3 stage, this is called 3 stage. So, impellers are mounted in a common shaft, so that this is let us say this is 3 stage or 2 stage, this is 2 stage, this is 2 stage. There will be a stator which will be hanging from the casings or fixed to the casing, and there will be rotating rotor which is rotating with the shaft. So, this is impellers, which a few impellers are mounted on a shaft only to rise the pressure and to prevent shock loss, so that efficiency of the machine can be increased. We will discuss a few cases, degrees of reaction whenever we are having staging 2 stage or 3 stage, and and what is also known as cascading, probably in one of my next lectures. So, with this I stop here about this discussion about radial equilibrium of an axial flow machines, and we will continue our discussion on the next topics, that is the series and parallel operation of a pump, and we will try to work out at least a few problems. Thank you.